This is 11.2. This is simplifying radicals. There are 3 laws when simplifying radical expressions. Radical expressions just means there's going to be a square root in it somewhere. First rule, law number 1, there can be no perfect square factors inside the radical. That's what radicand means. You are basically looking for numbers to divide by 4, by 9, by 16, by 25, so on and so forth, those perfect squares. If your numbers can divide by that, they got to get square rooted. Law number 2, no fractions inside the radical. You cannot have a fraction inside your radical problem. And law number 3, no fraction answer can have a radical in the denominator. You can't leave any of those alone. The reason that we're doing this is so that we get exact answers and not just our rounded off estimations. In chapter 11, principal, in chapter 11, we are only considering the principal or the positive root. Now the square root of 16 just equals 4. It doesn't equal positive or negative 4 until we get to 11.5. So right now the positive root is the only one that matters. All right, for example, oh, here's that again. So for example, here's how we would simplify this expression. Radical problems inside of square root can be split into the square root of those two things as a multiplication problem. You can split it apart. The reason that we would want to split it apart is because the square root of 9 equals 3. We can simplify this further. So remember, law number 1, we can't divide by a perfect square. 2, no fractions. 3, no denominators with a radical in it. So if you look at example 1, you have 12 times x squared. Well, I can change 12 into the square root of 4 times the square root of 3 and times the square root of x. I do that because x squared, sorry. I do this because the square root of 4 I can actually solve. It's 2. I can actually solve, I can't solve the square root of 3, and I can solve the square root of x squared. X squared and square roots are complete opposites. So that just means plain old x. Well, now my 2's on the outside of the radical, my x is on the outside of the radical. Let's put those together, and we get 2x times the square root of 3. That would be your simplified version. Let's talk a little bit more about square rooting variable terms. So the square root of x squared equals just plain x. Well, think about what x to the 4th would mean. X to the 4th means x squared times x squared, right? That's the square root of x squared times the square root of x squared. Well, this is x, and this is x. So this actually means x squared. So the square root of x to the 4th is x squared. Think about what x to the 6th would be. That's x squared times x squared times x squared. Look at how many I have there. I have x to the 3rd. Remember, radical problems are trying to figure out, square root problems, so like the square root of 16 is trying to figure out what times what equals 16. So the square root of x to the 6th is trying to figure out what times what equals x to the 6th. Well, x to the 3rd times x to the 3rd is what equals x to the 6th. The only time this becomes weird. Here, wait, let's make sure we got this. So the square root of x to the 10th would be x to the 5th. When this becomes weird is when it's not an even number anymore. When it's not an even number anymore, remember we can break it apart into our multiplication problem. That I can solve, but this I can't. That would be the answer to that. X times the square root of x. So like x to the 5th, if I square root that, I can change that to x to the 4th times the square root of x. And I know that the square root of x to the 4th is x squared times the square root of x. Any even exponent, you're just going to divide that exponent by 2. An odd exponent, you're going to have 1x left over, and then the exponent divided by 2 on the outside. So if that makes sense. So 4 is the biggest even number I can divide by 2 on x to the 5th. So there's that with the square root of x left over. And it's going to happen like that every time. Remember your perfect squares. They're in the back of the book if you don't remember them. So if I can split a radical expression into two multiplication problems, I could actually put it back together. So if they're both under radical signs, I can multiply them back together. The reason I would want to do that is because 18 times 2 is 16, and I know the square root of 16, which is 4. You can go about that answer this way, or did you notice that the square root of 8 could be split into the square root of 4 times the square root of 2, and then times the square root of 2? Well, that gives me 2. So the square root of 4 is 2. And if I take the square root of 2 times the square root of 2, that's pretty much like the square root of 2 squared, just equals 2. And then, hey, we still get an answer of 4. So on letter B, 2 is on the outside of the radical, and it stays outside the radical. But the rest of it, I can multiply together, times x. And if I do that, now that's 5x to the 4th y. All right, my 5. Can you divide 5 by any of your perfect squares? 4, 9, 16, 25, 36? No. So 5 has to stay inside the radical. But x to the 4th, that one I can square root, and it gives me x squared when I square root it, and now that's no longer in my radical. But I can't square root the y either. This is my final answer. That is as simplified as I can get. Okay, these problems got a little carried away, but let's make up our own. Let's do the square root of 40x to the 5th. Remember your rules. I can't have a number inside my radical that's divisible by one of my perfect squares, which this one is. 40 is divisible by a perfect square of 4. And so that's 4 times 10. And if I square root 4, that's 2 on the outside and the square root of 10 on the inside. Now, x to the 5th is the same thing as x to the 4th times x. And the square root of x to the 4th is x squared with x on the inside. That would be our simplified answer. 2x squared times the square root of 10x. Because I can split the 40 into 4 times 10, which is 2 on the outside, 10 on the inside. X to the 4th and x make x to the 5th, and the square root of x to the 4th is x squared. X stays inside the radical. This problem here was the square root of 10x times the square root of 5x to the 6th. Now everything is under the radical, so I can actually multiply all of this together. So I did 10 times 5 to get 50, x times x to the 6th to get x to the 7th. Now 50 I can split into 25 times 2. I don't want to split that into 5 and 10 because I can't square root 5 and I can't square root 10. But I can square root 25. And the square root of 25 doesn't start with the 2. It's a 5. And then the square root of 2 is going to be on the inside. Now my x to the 7th, I can think of that again as x to the 6th with an x. And remember, the square root of x to the 6th is actually x to the 3rd with one x left on the inside. And that would be my simplified answer there. So that's how you deal with law number 1. Law number 1 is simplifying so there's no perfect square inside the radical. Here is law number 2. Law number 2 says there can be no fraction inside the radical, so here's what you do. Split the radical up. Split the radical into the radical of the square root of the top number, square root of the bottom number, and then we solve it. The square root of 4 is 2, square root of 9 is 3. So if you see this problem, the square root of 11/49, split up your square root. The square root of 11 divided by the square root of 49. And I can solve the square root of 49. Can I simplify the square root of 11 to divide it by any of my perfect squares? Nope. Doesn't divide by 4, 9, 16. So that's my final answer. Here, split up your radical, t squared and 36. And I can square root both of those. Square root of t squared is t, and the square root of 36 is 6. Done and done. The fraction is pretty much the easier one of all of these. All right, so let's take a look at these. Go ahead and pause the video, and then we will come back with the answers. Let's see how you do. All right, how'd you do? My answers are circled here. Remember that the square root of an exponent, we divide that in half. Square root of an exponent, divide in half. And there can be no number left inside the radical that can divide by a perfect square. I know 15 you can divide by 5 and 3, but can you divide it by any of your perfect squares? No. So it is simplified. Okay, here is law number 3. Law number 3 says there can be no denominator that has a radical in it. And the reason is we don't like to divide by irrational numbers, and yes, old dead dudes decided this was the case. So radical in the top, no problem whatsoever. Radical in the bottom, not going to happen. But you remember what gets rid of the radical problem? What makes it disappear? Well, if I take the square root of 5 times the square root of 5, that's basically the square root of 5 squared. That's going to give me a whole number rational value of 5 for the denominator. But when you're making equal fractions like we're doing here, I'm simplifying my fraction pretty much. If I multiplied by the square root of 5 on the bottom, I have to multiply by the square root of 5 on the top. And now I have the square root of 2 times the square root of 5, both square roots. And that I can simplify. And there we go. So what gets rid of the square root of 7r in the denominator? Multiplying by the square root of 7r. Leaves you 7r in the denominator, but if you multiply the bottom by the square root of 7r, you have to multiply the top. And 1 times the square root of 7r is just 7r. And there's your final answers. That is law number 3. So here, take a look at this example. How would I get rid of that? Multiply the bottom by the square root of 6. This is 7 times the square root of 6 over 6. Here, I'd have to multiply by the square root of 5a, multiply the top by the square root of 5a. That's the square root of 15a. Can't do anything to simplify that. Over 5a. Done and done, and I hope you enjoyed today's lesson.